All right, it's time. Let's continue. Last time we were talking about damped harmonic oscillator. So all right. So basically the derivation is if you have a damped harmonic oscillator, if you have a harmonic oscillator, it's basically y prime prime my equals negative ky by Hooke's law. And then for damped, you basically just add the friction. Okay. We divide by m and we write everything. We end up with something look like this. That's what we had for damped harmonic oscillator. We then try to solve it. We kind of have the phase plane with the phase line, phase portrait. When p equals 0, the solution looks like a circle or ellipse. If p is bigger than 0 but small, we start to have something like this. Okay. And finally, if p is big, we have something goes to 0 right away, like that. Okay, that's the phase portrait. From here, you can see other than the first case, as long as you have something damped, basically what's going to happen is eventually that thing just reduced to no movement, no velocity, because you lose energy as time goes by. Eventually you have 0 energy. Okay, then we talk about how to solve this. We have y square, y prime prime, plus py prime plus 2y equals 0. We pick p equals 3 and q equals 2. What we end up is we let y equals to a special kind of form, which is e to the st, exponential. T is a variable and s is a function, is a constant. Then what we end up with is we solved it by plugging it in. With a 3 plus 2 e to the st equals 0. So we end up having e to the st, s squared plus 3s plus 2 equals 0. If we assume the solution look like this. Okay. After that, we end up solving it because this part is never 0. So we have s equals -2, s equals -1. We have two different solutions corresponding to e to the -2t, or y equals e to the -t. That's what we got by solving the quadratic equation. And then we stop there. Okay. Now we want to do some detailed discussion here. The first one is we have two solutions. Do you have a third one? Do you have a fourth one? Do you still have more? Okay. The answer is the following. Number one, because the system is linear. Number two, because it's homogeneous. Then what's going to happen is if this is a solution and this is a solution, then everything looks like a linear combination of these two. Any linear combination will also be a solution. So how many solutions do you have? You have infinitely many. As many as a two-dimensional vector space. Great. Number three. Second. Because it's second order, not only you have a lot of solutions, because it's second order, this also represents all the possible solutions. You don't have anything other than this. Because second order, you have two degree of freedom of constant. You already have two constant, so that's enough. We call this the general solution. Okay. So through solving a quadratic, you actually find all the possible solutions of this particular problem, particular choice of 3 and 2. That again corresponds to a superposition of your solutions, which is still a solution. That's number one. Number two. Okay. What are some other implications? Well, then we need to go back. For this case, we do have s squared plus 3s plus 2 equals 0. Okay. We have two solutions. We have two different solutions. Then automatically, what about in general? What about any p and q? For example, what's this? Which a different choice of p and q. Okay. You can make a 4 here, you can make a 5 here, you can pick any numbers. So how about we just pick a general number? And still use the same trick. Then we will have s squared e to the st. This time not 3, but p times s times e to the st plus q times e to the st equals 0. Factor out the same thing. Okay. Before we have 3 and 2 here. Now we have just a general thing, which you can see it's a quadratic with coefficient the same as what you have here. That basically means this is always solvable as a quadratic equation. You just need to find s by solving quadratic. For any p and q you put in, then of course, you start to ask, can things go wrong? Okay. This date all the way back to quadratic. When you solve a quadratic, what can happen? Well, 3 cases, remember. Number 1, 2 distinct real solutions. Like the -2 and the -1, the answer is e to the -2t, e to the -t. This is great. And if you do all the possible linear combinations, you have all the possible solutions. All right. What's the other solution, the situation? Well, if you solve a quadratic, it's possible that you only have one real solution. It's possible, for example, what's the problem with that? Well, number 1, This is certainly a solution. So there's no problem with that. Okay. The true problem come from my general solution should have two constants there to form a linear combination of two linearly independent functions. So I can span the whole solution space. Now I only have one. I don't know what to put here. If I only have one, it certainly doesn't make sense for me to put this one for twice. Then you can just merge them to give them only one constant, right? Still make sense so far? Okay. Those kind of cases, we call them degenerate. Later, actually not later, in other books, you may find the thing you need here is just another one. And for that one, you just need to do this times another t. You can verify by yourself. This one also satisfies the equation. Okay, this is something you manually created yourself by timing a t. Then you have two of them. Then you have all the solutions. You're fine. Sounds good? All right. We still have the third case. What's the third case? The third case is you don't have a real solution. That is when you do b squared minus 4ac, it's less than 0. So when you take the square root, you definitely have I. That's when you have two complex solutions. For example, y prime prime plus y prime plus y equals 0. Plus s plus 1 equals 0. You have to have an I there. That means for some special P and Q, you may have complex solutions. Sounds good? Then what's your solution? Well, my solution is e to the st. And I just computed s, so my answer has to be this. Then all my possible solutions are nothing but C1, this, okay, plus C2, this. Sounds good? This is easy. The harder part is actually, how do I understand this? What do you mean by this solution? Okay, what do you mean by you put a complex number on the exponentials? What do you mean by that? Well, let's take one of the examples out. This is basically e to the negative 1/2 t plus, we decompose into real part and imaginary part. That's doable. Now, because it's plus, we can decompose into this times Or let's put I here. Still okay? Question. I don't know if you guys have learned about this. Do you know what this means? If you put a complex imaginary number here, have you seen a formula look like this? Cosine theta plus I sine theta. That's Euler's formula. So this is actually cosine theta plus I theta. That means this one is nothing but not cosine theta, cosine this. Okay? You still have the other one. You can also decompose this one. You can see they're basically the same thing, except for when you have a positive here, you have a negative here for the second one. Okay, so let me just copy for the second one. Do minus this, which is nothing but e to the negative 1/2 t cosine negative square root 3 over t, which you can actually absorb like this. That's what complex number gave you. You have a real part, you have an imaginary part. The real part is just real part. The imaginary part, however, is going to give you cosine and sine. Sounds good? Cool. In order to write down your solution, then what you should do is you start with this. Okay, you start with this. Then you realize both of them actually give you this. And cosine and sine. Okay. The difference is the first one is a plus, the second one is a minus, but either way. Then I claim taking all the possible linear combinations of these two is the same as taking all the possible linear combinations of these two. Because number one, they're both two-dimensional, linearly independent. Okay. Number two, you can represent both by these two. So it's almost like a change of basis. Okay. Then all our solution can be rewritten into a better form. This time, no complex number, but, or let's say, even better, e to the negative 1/2 t cosine plus sine with a C1 and a C2. So when you have complex, instead of using basis of exponential functions with complex number, use cosine and sine instead. All right. Sounds good. What does the solution look like if you write them in this way? Well, remember, when we try to do the analysis, the solution looks like this. Number one, it has an oscillation part, which is like sine, cosine. Yes, it's here. Sine to cosine. Okay. But if it is sine to cosine, you should have something going forever. It's not damped. Right? It goes forever with the amplitude all the way equals 1. Where is the damped part? The damped part comes from here. Why? Because as t goes by, the amplitude of your sine cosine becomes smaller. That's why you keep oscillating, but weaker and weaker. So this is the damped part. Okay, so imaginary part give you oscillation. The real part give you the damp. Sounds good? Now think. Where does the damp part come from if you solve this? I picked a special P and Q, right? If you really solve it, you have S squared plus PS plus Q equals 0. Your S is going to be negative P plus minus whatever divided by 2. Okay. This part is going to give you something with I, right? The real part is going to be just this. So of course that's going to be your damped thing because P is taking care of the friction. That's exactly where the damped thing comes from. Sounds good? All right. Question. The real part takes care of the damped. That means the real part is always decreasing. You will never have something shake bigger and bigger and bigger and bigger. You will never have that. Still okay? But in theory, in mathematics, if you have something which is e times 2 to the t, it's very possible that you have something which is increasing, shaking more and more crazy as time goes by. It's possible, right? Okay? So why can't that thing happen? Now you need to go to this one. If you want the real part to be positive, which means you keep shaking bigger and bigger and bigger and bigger, it's not damped, it's amplified. Still okay? You will require this part to be 0, bigger than 0. Because that's the real part. You want that thing to shake bigger and bigger, bigger, you better make this part to be positive. That means you have to make the P negative. But then if you do that, that means your friction is in the same direction as your velocity. Right? And that contradicts to physics. That's why if you have friction, it never gets amplified. Reason is because the sign of P is always positive. That's how we got the friction. Okay, so it's always damped. Even mathematically, okay, you can put a negative number for P, but actually in real life, the P is always positive. Damped, because P is always bigger than 0. Then you can think about other cases. Maybe P can be positive, but can be negative, but that cannot correspond to a spring mass with a damped oscillator. You need to have something else. It can't be friction because friction always slows you down. All right, that's how we handle this. We started with the damped harmonic oscillator. We end up with something like this, which is, where is it? Which is a second order linear homogeneous equation with constant coefficient. The solution we provided is assume your solution is an exponential with a constant. We solve for the constant, and then we end up solving a quadratic. Step 1 done. Sounds good? Step 2, when you solve the quadratic, what are you looking for? Because it's second order, you're looking for two distinct solutions, and then you're going to take all the possible linear combinations of these two. That will be all the possible solutions. Now go back to your quadratic. If you have two different real root, done. You have two solutions. They're linearly independent. Do the linear combinations. If you only have one, you have the degenerate case. You created another one. There's a rule to create it. It's pretty easy. We won't cover it here, but basically you just times t. And if you need one more, you times t squared. Okay. Number 3, if they have something complex, well, decompose them into real part and the imaginary part. The imaginary part give you cosine sine. The real part give you damped effect, because the real part is basically from complex number, how long your complex number is. Okay, that complete everything about quadratic. Make sense to everybody so far? Now let's push one step further. If you have questions, just read it. Okay. If nobody says anything, I'm just going to push it to the next one. The third thing becomes super interesting. That is 2 or 3. 1, 2, 3. Okay. 3. Does this one only work for quadratic, or can we do cube? Can you solve something like this? That's a differential equation. Okay. Let y equals e to the st, y prime, s e s t, y prime prime, s square e s t, y prime prime prime, s cube e s t. Put everybody in to the original thing. What do you got? Number 1, everybody has an e to the st, so I can take them out. Okay. Second, for the third derivative, I'm going to have s cube. For the second derivative, I'm going to have a square for the first and for the non. So how do you solve this equation? Again, this cannot be 0. Therefore, we set this to be 0. And we can solve it. I mean, it just takes some time. But we can solve it. Sounds good? What if I have y to the 5th? That's just going to give me a s to the 5th. Y to the 7th, that's going to give me just s to the 7th. So no matter what, if you assume this assumption, basically you're just going to have a lot of power. Sounds good? Okay. So this method, this assuming your y is exponential, this method works not just for quadratic. It works in general. Okay. Basically, you turn a differential equation into finding the roots of a polynomial. We just happen to solve the second order polynomial, which is a quadratic case, but for cubic it works. Actually, for any polynomial, it works. Like this. Sounds good? All right. Of course, this only works for a certain type of differential equation. So let's summarize. What is this? Number one, it has to be linear. Plus, minus, if you have a y square, everything got screwed. Okay. Second, all these things has to be a number. They cannot be t square or something like that. Otherwise, you have s and t in the same thing, right? You prefer everything here to be a constant. Therefore, not only it's linear, it has to be constant coefficients. Number three, this has to be 0. The reason is because when I set everything up to here, I want to divide this one. How can you divide that without changing the equation? That means the right-hand side has to be 0. So this only works for homogeneous case. Okay. So that's the general formulation. You see anything like that? You observe number one, linear, number two, 0 here, number three, you only have constant. Automatically, your solution, EST. Do it, you end up solving a polynomial of S. Okay, something like that. Linear, constant, 0, therefore it's doable. Okay, let y equals e to the st. So this one works for general cases. Can be any order. Okay, that's the first comment. Second, how do you solve the root of a polynomial? Here's the beauty. If you have an nth order ODE, for example, you take all the derivative up to the 7th order, then you are guaranteed you're going to have an nth order polynomial. The fact comes from e to the st. If you take the derivative for n times, definitely give you Sn. Okay, so you have the same nth order. All right. Now, if you're trying to solve an nth order ODE, for example, for second order ODE, in order to generate all the possible solutions, you need 2 solutions. And then you do all the possible linear combinations of them. Good so far? For third order ODE, how many solutions do you need? You need 3 solutions and then do all the possible linear combinations of that. Okay? So for nth order ODE, you need n linearly independent solutions. You need to have enough and then do all the possible linear combinations of them. That will be all the solutions. Sounds good? Where are you going to get them? Well, they all come from e to the st. So all the n-linearly independent solution come from the n roots of the polynomial. And this is beautiful because if you think about it, if you have a cubic polynomial, you definitely have 3 solutions, 3 roots. Okay, if you have a quadratic, you certainly have 2 roots. You have a 7th order polynomial, you have 7 roots. Okay, so you always have enough. Sounds good? All those roots, you will have real. Beautiful. That's just e to the some number times t. That's exponential. You are going to have complex. We just handle it. It's no big deal. It's just real plus an imaginary, and imaginary give you cosine sine. The only trouble is when you have repeated roots. For example, if you solve a 7th order, you have 4 roots. It's possible, but it doesn't mean that you have 4 roots. It means you have 1 root repeated for 3 times, or maybe 2 roots, each one repeated for twice. That's how you add together equal to 7, right? But then we talk about how to generate more from there by basically doing e to the st, t e to the st, t squared e to the st. You just keep generating depending on how many times the root repeats itself. We didn't go over why this is true. You can verify by yourself. Okay, take this one, put it back, it still works. All right. I would say this is the main result here. Then everything with harmonic oscillator, we just handle the most easiest one case. Okay, but it works in general. All right, any questions before we move on? That's beautiful if you think about it. If you have something look like this, before you even solve it, you already know this one's going to have a wave because it's either sine or cosine or a damped sine cosine. Okay, so that's why wave is everywhere. Okay, that's number 2. Now let's talk about the third thing. Has everybody heard about Krikov's law before from electric circuits? Okay, so basically what it says is, if you have electrical circuits, no matter how you do it, right? Yeah, I better draw something like that. Yeah, let's just do an easy one. Okay, then the total voltage is 0. Otherwise, your total basically means all your electrical potential should be balanced. Okay, for this to happen. That means something plus something plus something equals 0. And this represents the total voltage. That's the law. All right. So how many electrical gadgets can you have? If you go inside for the basic ones, you only have three things. A capacitor, okay, a resistor, and then the inductor. No more, only these three kinds. Okay, if you have multiple inductors, just merge them into one. Still okay? Now let's talk about the voltage each one provide. For capacitor, does anybody remember the formula? The voltage? Q divided by C. Okay, Q is the charge. Okay, C is the capacitor. Capacity, actually. What about resistor? It's Ohm's law, right? It's R times I. What about inductor? Well, inductor is going to be, how to say, L times I prime. Here, I is the current. R is the resist. Resist. Okay, and L is just the inductor constant. That basically means we only provide voltage if the current passing the inductor actually changes. So if you decrease or increase, this one is going to respond to make you slow down. Everything makes sense so far? If you haven't heard about this before, you can look it up. It's really easy, okay? But if you're from physics, you see this automatically. Then what you need to do is just put this one plus this one equal to 0. That's going to be the law. The total voltage is 0. Okay. Now let's just do one more step. We have Q here, we have I here. But we do know that I, the current, is the changing rate of the charge, right? So I is actually dI over dQ over dt. Or more precisely, it's actually Q prime. Putting this factor back into this, what you got is actually this. Q prime prime coming from here. Q prime come from here. And prof 1 over CQ equals 0. Now, if you divide L on both sides, I mean, you can do the same. It's not hard. You basically have Q prime prime plus a PQ prime plus a QQ. Yeah, that's a bad name. Let's change Q to be Y. Let's just change everything. Okay, don't use Q anymore. So basically divide by L, and you change your Q to be a Y. You end up with something Y prime prime probably constant times Y prime plus Q times a Y. You can figure out what the constant means by yourself. Okay. Then from here, you can see it's the same as a harmonic oscillator. If you know how to solve the harmonic oscillator, you know how to solve the electrical circuits. If you know how to solve the electrical circuits, you know how to solve the harmonic oscillator. That's awesome. Okay. How to solve it, you know how to do it. How to think about it, well, what do you think the solution is going to be? It's going to be a sine cosine periodic curve. right? Is it going to be damped? Or is it going to be oscillating back and forth? Well, it really depends on, do you have a P? Because the P is where your friction come from before, right? That corresponds in electrical circuits. Do you have a resistor or not? So this tells you if you have electrical circuits, if you lose energy, if you have a heat diffused from any of the gadgets, it's going to be the resistor. It's the same as friction. Capacitor, inductor, they don't lose energy. Sounds good. Okay, so we got harmonic oscillator from a spring mass system, but then we can actually, get something interesting about electrical circuits from it. Certainly, you start to have applications. Okay, for example, when you design a car or like an airplane, okay? Does everybody know what a sound barrier is? Like if you travel at a certain speed, your things start to resonate with the particles in the air, right? Okay, and then suddenly you're going to have a lot of oscillation. So the oscillation of this one, the vibration, that's called vibration, of the airplane itself, can be modeled by a harmonic oscillator. Okay, you can do the computation. Maybe you did it right, maybe you did it wrong, maybe you need to add in some constant, maybe. Okay, so eventually once you calculate everything, you claim this is going to work. You still need to test it, right? Once you do finish the calculation, you're going to test it. How do you do that? Number one, you can build an airplane with exactly the parameters you calculated, and according to your model, that thing doesn't break. Okay, you build that airplane, you put a pilot in or you don't, then you start to set this airplane at the speed you want and see if that thing breaks. If it doesn't, good design. And before you get the good design, you probably need to destroy hundreds of planes, okay, until you have the right number. Still okay here? Cool. Now what we just did is we proved harmonic oscillator can be also modeled by electrical circuits. So instead of testing it on an airplane, why don't you just test it on electrical circuits? And if that thing breaks down, it's probably $20 per piece. If it breaks down, end up melting something, just let it be. Okay, so this is a typical application of how to make the connections. You want to test the airplane, you want to test the bridge, see if that bridge breaks down. Okay, you don't want to actually build the bridge and test it. Instead, what do? You build electrical circuits, okay, and see if anything goes wrong there. That would be way cheaper. Of course, this relies on the underlying models of the two different phenomena are exactly the same. So you can test one on the other. If you think about it, that's beautiful human wisdom there. Okay, how on earth do you know that the vibration of an airplane is the same as an electrical circuit? That's beautiful. All right. That's roughly everything about harmonic oscillators. Okay. Any questions so far? It's a very rich topic. The book stops here. Actually, it stops even before that. Okay. That also means our exam will cover everything up to here for this section. And of course, the Krikov's law, and of course, anything below that. Okay, so only these two parts will be covered in the exam if you're looking for exercises. Okay, you won't be able to find the exercise of anything in between in the book. But I thought it would be really nice for you to know everything in between, because that's the whole picture of what's going on, especially the complex numbers. And that's how you got everything. One, two. Okay, number 3. All right. So far, everything we learned is damped harmonic oscillator or undamped. We always set this one to be homogeneous. Or let's say no force. So you have some oscillation, you have some vibration. It's basically free. Okay, you start it and you leave it alone. No external interventions. If you have originally have an electrical potential, you don't interfere it with another electrical potential. Okay, you just leave it be. Of course, we can just talk a little bit about forced harmonic oscillator, which basically means we don't pick a 0. Instead, we pick some function there to interfere with that thing a little bit. Let's not even consider the damped. Let's just consider the original one with no damp, which give you y prime prime plus k over my equals 0. Okay. Now we solve it. We solve it. We have cosine square root of k over m t, sine square root of k over m t, and then all the possible linear combinations of them, assuming we already have the linear knowledge. But now it makes sense for me to take this out and call it the frequency. Okay, actually, the intricate frequency, which basically come from the spring. The mass. Okay, we call it omega 0. So if you have a system with no external force, this is how that thing is going to behave. This is the frequency. Okay, so you can rewrite the equation into this. Square y equals 0. All right, that's good. Our job now is we're going to erase this 0. We are going to apply force to the whole system from external resource. Okay. There are all kinds of source we can apply. We can apply a force constant. We can apply a force with respect to t. We are particularly interested in interfere it with a periodic force with a different frequency, okay. Omega t, not omega 0. You can think about it, it's like an alternating electrical field, just alternating all the time, which is sine cosine. Okay, that's very common for you to apply in real life. And see how that's changes the behavior of the whole thing. This is clearly non-homogeneous. So the solution won't be just a simple find two solutions, linear combinations, okay, because it's non-homogeneous. But we will talk about it later. Okay, that's all for today.